Hello all, welcome to the video lecture series for the subject operating system. Now I am going to explain you all about what is the program for round robin scheduling for the same arrival time and different burst time. Right. Let me tell you what is round robin in CPU scheduling. This is the algorithm where each process is assigned with a fixed time slot. We used to call it as time quantum. It is by default, it is a primitive version of the first come first serve basis. Each and every process will be treated, right? By default, it is a primitive scheduling, CPU scheduling, right? Round robin CPU algorithm generally focus on time sharing technique. Okay, it's always based on the time sharing. Each and every process will get an equal time of process execution. The period of time for a process or a job is allowed to run in a primitive method is called time quantum. That is a point here. Okay, so it allows to run in a primitive method. So whichever the primitive method, that is next process which is coming and the process which is already executing inside the CPU. So everything will be based on the interruption. So if it is interrupted by the next process which has the lowest priority, or else the highest priority, lowest burst time, and etc., whichever the whichever the priority you give, that is quantum here, right? So here each process or a job present in the ready queue is assigned to the CPU for the time quantum, and the execution process completed based on the time ends, right? Now listen, here we have an example. That example has process ID, arrival time, and burst time. So totally 5 process here, arrival time is here, burst time is also here, right? Now this has been pre-written for easy understanding. So now time quantum has been given as 2 units. So each and every process can take only time quantum of 2 to take the CPU for the run execution time, or else we can call it as runtime. So it will run for only 2 seconds or minutes based on the unit, right? So the time quantum is already fixed. So let's draw the Gantt chart. Now by seeing this Gantt chart, you can able to identify how this process has been taken this chart and why P1 is coming repeatedly after P3, why P4 is not coming. We will be getting all the answers now, right? Now listen, first P1 is coming inside. Why? Because the arrival time is 0 here. So based on that, P1 is coming inside, P2, P3, P4 and P5. Now we need to check what is the arrival time the last process is getting, that is 4. So if the arrival time is 4, we need to draw the ready queue for all the process which is interrupted by the other process based on the time quantum. I told you already, time quantum is a method, like it is running a primitive method. The time quantum is already prefixed here because it is a primitive method of understanding. That's a point, right? So during the time, each and every process will end exactly based on the time quantum. We'll have a clock here, we have a timer here. Each and every process will take only 2 seconds or minutes based on the capacity, right? Right. So let's get into the process directly. So P1 is getting into the chart first because its arrival time is 0. So you all know that time quantum is only 2. So P1 can take only 2 seconds to run its burst time. So totally it is 5. So after subtracting 2 quantum with this, it will reduce into 3, right? So it will take only 2 capacity, and it is running over here. By the time when 2 is arrived, by the timer of 2, so process 1 is completing its task, process 2 has been arrived, process 3 is also arrived. So when process 1 is running inside, by the timer 1, process 2 is coming inside. By the timer 3, process 3 is coming inside. There you can say process 3 is coming at timer number 2. So these are all in ready queue. That's a point. I want to mention a very clear vision here, that is ready queue is very important here. Based on the ready queue only, this diagram, this Gantt chart has been derived. So I told you already, P1 is currently running. By the time it takes 0, by when P1 is reaching the timer, P2 is coming inside because the arrival time for P2 is 1. So it is in the ready queue. When the timer comes exactly at 2, so again P3 is coming inside, it is in the ready queue. So by the time when this particular P3 comes, so the timer is 2. At the 2, timer 2, the P1 exits this CPU. Why? Because the time quantum is only 2. So every process can stay inside for only 2 time slots. Right? If the bus time is very low, it cannot stay inside for 2 seconds or minutes. Once the bus time is low, it has to leave this particular CPU. Okay, now P1 exits exactly at 2. So by the time P2 is in a ready queue and P3 is in a ready queue, so at the time of 2, you can check it. At the time of 2, no other process comes, only P1, P2 and P3 is there. So here you can check it. P1 has been taken only 2 seconds to execute the task. So remaining 3 is there. Why? Because 5 is the bus time. Now P1 has to get into the process again because it needs CPU again for completing is the remaining bus time. So what it will do, when P3 comes, the timer is exactly 2. It is already, P3 is already in the timer. It is in the queue, ready queue. This is the ready queue which occupies the CPU. Now P1 exits at exactly 2. So by the time who are all inside this queue, P2 is here, P3 is here. So by the time this P1 exits this particular CPU, no other process arrived except P1 and P2 and P3. So what this P1 will do, it will be placed in the queue after P3. I hope you understand this point. So this is how, if you have any confusion in this, then your diagram, that is Gantt chart, will be wrong. Right? So this Gantt chart will be completely drawn based on the ready queue. The very important point here it is to understand how this ready queue works. If you are very confident enough to see why this ready queue has been made in this form, then this Gantt chart is going to be very simple for you to derive. Right? So now P2 comes inside. So here P2 has a burst time of 3, but the time quantum is only 2. Whenever the timer reaches, here you can see the clock, whenever the timer reaches 2, the current process which is acquired, the CPU has to leave the CPU. So when the P2 is leaving the CPU, you can check it. At the timer 4, this P2 is coming outside and still it has one more burst time to complete because it is taken only 2. Time quantum is only 2, right? So it has been taken only 2 seconds to complete, but still it has one more burst time to complete, right? Now after this P3 is exiting, where this P3 is exiting, you can check at P2 is coming inside by the time it is 4, and by the time whenever this 4, that is P2 is exits at 4, all P1, P2, P3, P4, P5 has been arrived. You can check it, right? All this process has been arrived. Now what to do? So P2 is exiting from here at the timer 4. Okay, now let's draw one more queue. I am just repeating that queue. P2 is inside now. Who is after P2? P3. I am drawing the same time. Same diagram here. So again now P1 is here. It is in the queue. And who comes next? So again P4 is coming at 3. So still when the timer 3, still this process 1 is running inside the CPU. Process 2 is running inside the CPU. Sorry. Process 2 is running inside the CPU. You can check it. So after this 2, when it is reaches 3, process 4 is coming. So process 4 will be in ready queue. I hope you understand this. Right? I'm just drawing the ready queue, except if the ready queue, you are okay with the ready queue, then it is simple for you to derive this Gantt chart. When this P2 reaches the timer 4, and at the same time P5 is also arrived. So P5 is also in the ready queue. So now what left? When P2 is exiting, it was interrupted by the next process. Why not next process? It was interrupted by the time quantum. You can check it. Time quantum is only 2. Correct? So when the time quantum it reaches, and it still have one more burst time to be completed. Anyway, it is exiting from the CPU because the time quantum is automatically making this process 2 to exit. So when the process 2 is exiting, you can check it. Overall inside this ready queue, P3, P1, P4, P5. After P5, this P2 will be placed in the ready queue. Right? So this is how this ready queue has been made. Based on this ready queue only, this Gantt chart has been done. Right? Now see, After this P2, so here it is, P3 is coming inside. What is the burst time for P3? Only 1. It doesn't mean that the P3 has to stay inside for 2 seconds. No. If the burst time is less than the time quantum, what is the time quantum here? 2. If it is less than the time quantum, whenever it completes this task, it will never reside inside the CPU. So no process will be idle inside the CPU, right? So the CPU will make the process exit. So when process 3 is getting inside and it is running for only 1 second because the burst time is 1. So next process is P4. You all know that because sorry, next process after P3, who is in the ready queue? P1, right? I hope you understand. From this particular queue I have drawn this little bigger. So this, after this P3 is exits, it is not going to wait in the ready queue because P3 complete its task. So P4 is getting in, sorry, before P4 we have P1 here. I told you how this P1 comes here, right? So now P1 is getting into this particular Gantt chart and P1 is again executing for 2 minutes. By the time it has 3, now it has 3 has been become 1. So when this process 1 has yet to complete one more, right? You can check it over here. Process 1 yet to complete one more burst time. Again, it will come into the queue. Who are all waiting when P1 is getting inside? P4 is waiting. P5 is waiting. P2 is waiting. And the only next process is P1, which is coming after this P2. So P1 is also now in a queue. So after P2, the P1 has been getting inside, right? So after P1 is getting outside and ready in the queue, who is next to P1? You can check it. P4 is coming inside. How long this P4 will be executing? It will execute for 2 seconds and its burst time is also 2. So this process comes to an end. So after this P5 is coming inside because 1, 2, 4 is also executed. P5 is coming inside. Now P5 is coming inside. What is the burst time? This 3. Now it will take the CPU for only 2 seconds. And when it completes the 2 seconds, it has to complete one more because it has burst time is 3. When P5 is coming outside, you need to see here. Who are all in the queue? See, P5 is running inside. And after P5, who are all in the queue? P2 is there. So I am just taking this down. P2 is there. P1 is there. So now P4 is yet to complete one more burst time, right? So after P1, P2, P1, this P5 is coming next, right? So you can check the same thing has been written in this time. So whenever it has to complete the task, it will see the ready queue, who are all waiting in the ready queue. After next, it will be placed based on the next chance to be adopted in the Gantt chart. So P5 exits, again P2 comes inside. How many left for P2? Only 1. So P2 will take 11 to 12, only 1. After this is also over. So after P2, who is coming inside? P1. P1 also only 1 left. You can check it. Only 1 left. P1 is also completing 12 to 13. 12 plus 1, 13. After that, so you can check it. P2 over, P1 over, P5 is coming inside. How many seconds remaining for P1? You can check it over here. Sorry, P5, only 1 second. That is also over. So now it starts with 0, ends with 14. Right? So here you need to mention, you need to listen to the only one perfect ending of understanding is how this ready queue is made. That's a point. Rewind this video and check that. So if you still don't understand, please comment me. I will answer your doubts for sure. So here is the process, right? So I have written whatever I have explained. I have written in this particular understanding, the similar understanding way, right? So time 0, who comes, time 1, who comes, time 2, who comes, who is the next, ready, and everything has been written over here. Whatever I have explained here, I have written here. Okay, so now let's get into this particular process, that is TAT, calculating a TAT. Now TAT, total turnaround time, is equal to completion time minus arrival time, and waiting time is equal to turnaround time minus burst time. So let me show you how this P1 is happening here. P1 completion time. What is the completion time for P1 here? See here, P1 executed here, and also here. What is the completion time? The maximum time it takes to complete has to be taken. So P1 completes exactly at 13. So P1 initially completes at 2. Again P1 completes at 7. Again it completes at 13. We need to take the maximum. This is the point you need to understand and note. Okay. So here it comes 13 minus arrival time for P1 is 0. So answer is 13. Now, what is the waiting time for this P1? That is, waiting time is equal to turnaround time minus burst time. So P1 is equal to, what is the turnaround time? We found 13 is the turnaround time. 13 minus burst time for this P1 is 5. Total burst time, that is equal to 8. So this is how all the process 2, process 3, process 4 and process 5 has been done. You need to understand only one thing, that is how this ready queue has been made. So this is the overview of this particular problem. How this ready queue has been made, this is the overview, you can check it. What is time quantum? I have explained clearly how the ready queue has been made. I hope I made my best to solve your doubts by drawing this particular ready queues here. So you need to understand why this P1 is coming after P3. That is very main part you need to understand. Why? Because after P3, P4 has to come. Why this P1 is coming inside? I have explained it very clearly. I have drawn the that is ready queue also here, and also you can check it one more time, right? So this is how this round robin scheduling has been done. By default, round robin is a primitive, okay, and it will always work with the time quantum. I hope you understand the video. Thank you so much.